This is a video about day 18, but I want to briefly talk about day 17 before I start, because I'm skipping over this, and it was a pretty interesting day. It's essentially, I don't know if there's a smarter way to do this, but I saw this as just asking us to do Dijkstra's algorithm with this interesting constraint where the graph that we're searching over is not the literal graph that you see on your screen, but actually the graph that is the location in space and also the uh, duration, the number of tiles that we've traveled along that space. So actually, there's like uh, for each cell here is not a single node on the graph, but there's actually like 10 nodes on the graph for pairing this with the rate that you've gone so far, and actually the direction that you've gone so far. So pretty interesting. But Dijkstra's algorithm and other like similar graph search algorithms really kind of need a heap, and Janet doesn't have a heap in the standard library. That is uh, much fancier of a data structure than is available out of the box. So in order to solve day 17, I actually implemented a min-max heap in Janet, and I just wanted to like briefly plug it because I didn't know min-max heaps existed before I wrote this. I was reading about how heaps work, and I came across this. So I've heard of min heaps, I've heard of max heaps. I didn't know that you could stick a min and a max heap into a single data structure. And the way it works is kind of alternating levels of you have a min heap, and then all the child nodes of it are a max heap, and all the child nodes of that are a min heap, and like each other level alternates the way that it sorts things. It's really interesting. I don't think I could recreate the min max heap. It was a little bit mind bending to implement because uh, the way that it flips every other level kind of changes everything about all of it. So it was much trickier than just implementing a single directional heap, but it was a lot of fun. And we talked about comp on a previous video, and this heap is also comparator based. So you can use the same uh, comp short like comparators to decide how your heap is ordered. You're not um, using something like the before predicate that Janet's native types use. So that's how I solved day 17. And implementing the heap was the bulk of the work of the problem. So once you have that, it was kind of just Dijkstra's. But this is a video about day 18. So day 18, I wanted to do this one because it has a really interesting solution. And it actually, I learned this trick when I was after doing day 10. So I solved day 10, which is this gives you this pipe maze, and then it asks you to find the interior area of the pipe maze, the like enclosed by this pipe. And I saw this in a really dumb and complicated way. I did like a flood fill over the edges of this graph so that you could do the flood fill like in between pipes like this. And turns out there's a really easy way to solve this, and I learned about it from a coworker after I had solved this day, and I'm really glad that I did because I could just use it on day 18, and it made this problem pretty straightforward. But there's still some interesting parsing and some a new peg trick that we haven't seen before. So let's try to implement it. I haven't practiced this one, so it's going to be another kind of slow one, but we'll start as always with a peg. Split on new lines, and a line is direction, and then a space, and then, yeah, I'll call it a count. And that's it. We're actually, for part one, we don't care at all about anything after this. We just want these first two numbers. So a direction is a single character. I'm going to capture a single character, and then I'm going to use something that I haven't used before, but you can pass a dictionary to replace. So replaces this function is called replace. Usually write it with a slash, and you can pass it a function. You can pass it a dictionary, by which I mean a table or a struct, or you can pass it any other value. And what it does is totally different depending on which of these three things you pass it. And I don't really love that about this operator because sometimes you might want to actually replace something with a function and you have to remember to wrap it in another function because otherwise it'll reinterpret it, but dynamic types. So I'm going to pass it a dictionary. I'm going to say if you captured an R, then that's going to be right. And I will define what that means in a second. D is down, L is left, U is up. And I'm just going to define all of these as, we'll say that up is, it doesn't actually matter what the, whether this is left or right, but, sorry, whether like positive or negative y is up or down, but similarly here, like left, of course, should be negative, but it doesn't matter. And right, so these are our little unit vectors for the directions that we're going to travel in. And then count is just our old friend number d plus. And we'll match that on the test input. See what that looks like. Looks all right. I, as always, want to group this and I forget. Okay, so here we have, we're going right. I'm just gonna look at it here. We're going right 6 spaces. Okay, and we want to find the area. This is like, we start it at the origin at 0, 0, and we say go right 6 places, go down 5 places, go left 2 places, and we like draw out this shape, and then we want to find the area of the shape inside of it, the area of the enclosed space. So the trick for doing this, for calculating this area, is it's called the shoelace theorem, and I probably should have pulled up the Wikipedia or something. But what we're going to do is convert these into vertices in space, and then once we have all of the vertices, we can find the area of the enclosed shape. So that's not literally what the problem is asking us for, because the problem wants us to include the perimeter, so we can't just use the area, but knowing the area will allow us to easily calculate the value that it's asking for, which is not the area of the polygon, but the number of enclosed tiles that you're like digging through, which I think is like very similar to the area, but not exactly the same. So take solve, take the input, and we're going to write a few helpers in order to do this. So I'm going to peg match, peg test input. So these will be the instructions that we loop over. Let's call them instructions. And then what we want to do is find the vertices starting at 0, 0 and moving in each of these directions. So Janet has a function called accumulate, and accumulate takes 3 arguments. So it's like, I call this function scan. That's how I've seen it in other languages, but it's going to take a function that takes, it's going to take an initial state. So I'll say it starts at 0, 0, and it's going to take a list of things to iterate over. And then just like a fold or reduce, this is going to be like, this is our current position. And then this is the next instruction, which has a direction and a count. Perfect. And I always find these kind of hard to read. So we can actually, what we can do is like pass the instructions afterwards. It doesn't really work well because we have to pass 2 extras. Anyway, it's a little bit hard to read because we're splitting the arguments over multiple lines, but what we want to do is take the current position and then add to it the direction times the count that we're moving in that direction. But that doesn't work. Janet doesn't let you do this, and this is something that I haven't. I proposed to this a long time ago, and people weren't. It didn't get like a lot of positive feedback, such that I'm not sure if it would actually be accepted into the language. But I really just want to change this property of Janet to make this work. So you can't add tuples, you can't add arrays, you can add anything else in the language by overloading these operators, but there is no built-in definition of what addition means for arrays, and there's no way to provide a definition because you can't just implement this method like you could for an abstract type or a table. So you're just completely unable to add tuples. This is annoying. We're not going to solve this right now. I often just shadow plus and times so that they do work this way, but for this I'm going to make an explicit vec plus just to be kind of lazy, and because I only need this to work in 2 dimensions, I will just be lazy and only define it in 2 dimensions. So this will return plus x, oh my gosh, x1, x2, y1, y2. So that'll be my vec plus. And then I will also have a, call this vec scale. I realize that's not really, well, I'll be consistent. Vec plus and vec scale. And vec scale, how did I write this? Dir times count. So I'll take x1, just xy, and that'll be s for my scalar factor. This will be times xs times ys. And now I have to write vec plus and vec scale dir count. Just making sure I got the arguments in the right order. So this will be the vertices that I have. So let's try solving it. Solve test input, and I did it again. Solve test input. Okay, so these are the vertices that we pass through, and notice that we come back to 0, 0. And this is really important because accumulate doesn't include 0, 0 initially, so if it gave us like an open loop and expected us to implicitly close it, this wouldn't work, but it always comes back to 0, 0. We're always given a closed loop as our input, so we can use accumulate without having to like deal with the end of it differently. So that's the first step, but now I need to calculate the area of this. So make a function area that takes the vertices, and what we're gonna do is we want to look at like a sliding window of group 2, and Jana has a built-in function partition which will group something into windows. I think it's partition 2, 1, 2, 3, 4, something like that. But we really want like a sliding partition. So I'm gonna call this window 2. So window. So I'll take a count, and I'll take an index structure, and I'm gonna return this. I guess it can be an array. So seek I and range. See if I can write this without totally screwing it up. So I think I want to do the length of I minus the count is the number of these that we're going to have. Range 2. I'm just doing it with 2 in my head. I know that I want to go from 0 to the length of the array minus 1 in that case. So I in that range, and then j in the range 0, range 0 to count. And I want to return, well, I'm actually returning arrays of arrays, so I want to do this as seek j in range 0 to count, so that I get the nested array instead of flattening it all. I'll take in indexed I plus j, I want to say. Does that work? Yeah, so 1, 2, 2, 3, and 3, 4. I do link 3, 1, 2, 3, and 2, 3, 4. Okay. So window. So in window 2 vertices. So what this is going to give me is P1 and P2. let's go ahead and immediately unpack those. So this is like a little bit of a hairy pattern to look at, but the formula for the area, this is something called the shoelace theorem or the shoelace formula or something. We'll take the, I don't actually know if it matters which one we do, we can just do both, but the difference in x's times the sum of the y's is, I think, right? Let's just test that with the area of, so like 0, 0, 0, 5, 5, 5, 5, 0. What is that area? Negative 50. Well, that's probably actually correct. I just should have done it in a different winding order. That's clearly incorrect because it is this over 2. Or maybe right here, so I already have the multiplication. Okay, that's the one. So that's the area of this. So I can solve this by, instead of just the vertices, take the area of the vertices, and that gave me 42, which I don't actually think is the right answer. Because we don't include the perimeter. Or we sort of maybe do include part of the perimeter, but the thing that we actually want to do to, given these vertices, include the number of enclosed points in this is we're going to use something called Pick's theorem. And I think that's what it's called, Pick's theorem. So this gives us an equation that relates the area of this polygon to the number of actual vertices that are enclosed by it. And it only works if the vertices are all on integer coordinates, which they happen to be on integer coordinates in our case. So we can use this. And what I need to do is take the area of the vertices, the perimeter, I need the perimeter, which is going to be some loop of, we don't care about the direction, we just care about the count in the instructions. It's just the sum of the counts. And it's not enough to add the perimeter and the area. That gives us like way too many. I don't really know the area of the enclosed points. Like, I think the problem is essentially that we're treating this like a continuous value. So when we have this like grid, our points are either like the top left or the bottom right or something. So when we calculate the area of this, it's calculating the area of like, this counts, and we go down to like here. So we're excluding the ones at the bottom, but Pick's theorem will like rediscretize this area into the integral points. So Pick's theorem, it's an equation that relates the area to the number of interior points and the perimeter, but we already have, we know the perimeter, we know the area, and we actually want to solve for the interior points. So the interior points are we just have to like rewrite this equation in terms of I, and we get, it's the area of the vertices minus 1/2 of the perimeter, which is a word I can't type, plus 1. So that's the interior points, and then what we want to return is the sum of the interior points and the points along the perimeter. And that gives us 62, so we're not double counting the like points in the top left borders of the shape. And let's just check if that was actually right. 62. Okay. Now, part 2 is it's kind of designed to make sure that you used an efficient method to solve the first part, because it's asking you to do exactly the same thing, but with a different, much larger input. So this is going to be, whoops. Just going to refactor this slightly to be solve aux, I don't know, of peg match the input. So I'm going to make this helper solve aux, which takes, instead of the input, it takes the instructions, because the only thing that differs is the way that we parse the instructions. So that'll be solve. I should probably test it on the real input as well. Looks good. This up to my, closer to my peg. Great, and was that correct? 61, yeah. So solve 2 for part 2. All we're gonna do is change, I'll call this like peg 2. Changing the way that we parse the input. So now we're going to decode it. So the last digit here tells us the direction, and the first 5 digits are a hexadecimal number telling us the duration. So Janet makes this like really easy to parse this second one. So a line is now one character that we skip, followed by a space, followed by some number that we just ignore if we don't care, followed by a space, and then a brace, and then this is going to be count and direction. And just to keep everything exactly the same, I'm going to then rearrange them so that it's direction first and then count. So we're changing what direction looks like, and I have to look up what the actual mapping is. 0 is R, 0 is R, 1 is down, 2 is left, 3 is up. 1 is down. Oh, look, I put them in the right order. It's complete luck. And the count is, we're still parsing a number, but we're just going to say, so the second argument to the number is some peg, and it's going to advance this, and I'm going to give it the peg 5, which just says take any 5 characters. I'm not going to bother to say like only hexadecimal characters. Oh, and speaking of which, I need to ignore that hash character as well. And then you can optionally pass a second argument, which is the base to parse. So I'm going to say parse this in base 16. And now I'm going to just do this exact same test. And now I can see that I'm parsing much bigger numbers. And if I go down here, it looks like it failed to do something. Did I parse them in the wrong order? Oh, I have too much grouping because, yeah. Take that out. Yeah, okay. And then test input. This just scaled to the number of points, not to the size of the actual grid or anything. So we get this really big number, which seems to match. And we do this on the real input. We get this other gigantic number. So that was Pick's theorem, and I don't know when I would ever use this outside of an advent of code thing. It's kind of weird trivia, but I was glad to learn it after day 10. And the shoelace theorem actually seems like actually useful, and I wish that I had known that. I'm kind of surprised that I didn't, but it's this very, very simple way to calculate the area of an arbitrary polygon given points in some winding order. And seems handy, even though I don't know that I've ever wanted to do this. It's like a very elegant slice it into triangles and take the area of the triangles and add them up, subtracting out the some triangles that fall outside. Yeah, day 18, easy. A lot of just pegs make the parsing part pretty trivial, and then do a little math and we're done.